In Truss Lab I, the meter stick was horizontal. In Truss Lab II, we lowered the block and the meter stick was up at an angle. We measured the angle of the meter stick from the horizontal, which also goes there. And then we measured the angle from the horizontal up to the string. Remember, our goal is to predict the force of that spring scale. Well, let's suppose that the weight of the object was 2 newtons. Don't forget, we're going to add half the weight of the meter stick. So we have 2.25 newtons pulling down on the binder clip. Now, what do you think the string is going to do? Yeah, it's got to pull. Now, if you saw these two forces acting on the binder clip, that binder clip is going to want to move this way, but the meter stick is going to stop it. What's the meter stick going to do? Yeah, it's going to have to push. If that's theta 1, this is theta 1. Well, once I get rid of the apparatus, I now have a free body diagram. Let's suppose this angle is 30 degrees and that angle is 40 degrees. We can break these vectors up into x and y components. Now remember, we're looking for Fs, the force of the scale. How are we going to do that when we have two unknowns? Well, we're going to have to work with these components. How do you think these x components are going to compare? If the binder clip doesn't go anywhere, then these x components have to be equal. Well, we can calculate what these are by using these variables. Taking the cosine times Fs, taking the cosine times Fm. All I did was run the calculator, and we've got this equation. That's what I'm looking for. Oh, no, I have an unknown here. Hey, that's one equation with two unknowns. We're going to need another equation. Let's look at the y components. Now, in the last lab, there was only one y component, and that was from the scale. That held up the weight. But now we can see that with the meter stick at this angle, it's also helping to hold up the weight. So we have to say that both of these y components equal the weight. This is simply saying the forces up equal the forces down. Well, we can do the same thing. We need to get Fs in the equation, so we substitute the y component with Fs times sine 40. This y component, Fm times sine 30, and they're both going to be added up to equal the weight. The calculator gives us 0.6428 Fs plus 0.5 Fm equals 2.25 newtons. Well, again, we have one equation with two unknowns, but those same two unknowns are here as well. So we're going to substitute. I'll divide 0.866 into 0.766, and I'll say Fm is equal to 0.8845 Fs. Now I can take this value and put it in for Fm, right here. And I get force of the scale to be 2.07 newtons. Well, that's quite a job. Some people would rather put these vectors tip to tail and use the law of sines. It would probably help to enlarge the diagram. I'm going to start with Fw, and then I'm going to bring force of the scale down. I measure the 40 degrees from the horizontal, bring that down, and I go out to here because I know that the next vector has to finish the job to get me back to the start. Now the hard part is getting the angles right. If that's 30 degrees, this is 30 degrees. If that's 30 degrees, then this has to be 60. If that's 40 degrees, that has to be 50. And the last angle is going to be 70 degrees. I'll move the FW label up to here for clarity, and now I've got a tip-to-tail vector diagram. Now all we have to do is use the law of sines. We can say that 2.25 newtons divided by the sine of 70 is equal to Fs divided by the sine of 60. And we get 2.07 newtons, and that is exactly what we had using the component method. So either way you do the problem, you still should get the same answer. Now, some people find this easier. Some people get tricked up with all those angles. But you still, if you use this method, you still need to remember about the components. The force of the scale has a component to the left and a component up. And the force of the meter stick is also going up and over. Well, let's take a look at this. The X components cancel. The Y components going up equal the weight going down. So you can demonstrate that the components work the same way in a tip-to-tail diagram as with a tail-to-tail diagram. Now you need to go back to your actual apparatus and check to see what the spring scale read. This is the theoretical value. You would need to report your experimental value. Well, let's just say it was 2.15 newtons. Well, now you could go compare these two and report a percent error. And now to introduce part 3, the last part of the Truss Lab. Well, here we have the setup for Lab 2. All we have to do is move the clamp down the door. We're now going to have the string pulling down at an angle instead of pulling up at an angle. So let's say we have an angle of 30 degrees, an angle of 20 up here, with a weight of the object of 1.8 newtons plus half the weight of the meter stick. We have 2.05 newtons going down. Would you be able to calculate the force of the spring scale? Now, don't go building this, just try to solve the problem. Just watch the next video and you'll see that the technique is the same. There's nothing new here.